Okay, we're live. We are live. I'm pretty sure. Great, we have our tabs. That's our final cut. Look at this guy. Let's rearrange these tabs. Get this over to the end. Preview. Aerodynamics. I'm at the open courseware. You're playing. I actually have it loaded up. I don't know what I'm doing. Yeah, good. We did this yesterday. This is what we're working on today. Like I said, curl and vorticity. Let's plug this in. Oh, long day. Been quite the day today. A nice long build sesh for the product that, I don't know why. Like, day 10 here, it's just, or day 9 is when we're gonna end it, but let me go to YouTube Studio. That's great. We're live. Like I said, let's just get right into it. We're not chopping up anything. Okay, I'm pretty fed up with. Okay, let me start on a more positive note. I'm happy that I'm grateful that I'm able to pick the GPT brain. I'm able to explore or answer all my questions. However I want it. Look, I get to ask all of these questions, and it's just so clean and. Sorry, not clean. Forgive me. That's not at all what I mean. It's just not. I get to ask questions, get clarifications, get definitions, all in one context window, and and I'm grateful. Like I said, I get very good answers. Like a matter of fact, all the metrics that LLMs use is like I can match up to a PhD student in math or something like that. Like we can solve IMO problems. We can complete the SAT by ourselves. Like those kind of things. So academically, great. It's good. But I think I've spent the last 10 days doing these very long-winded sessions with a GPT, playing mental acrobats, and it refines, it gives you your definitions, it gives you your knowledge dumps. Yes. In the knowledge dumps, you have great things, such as maybe I understand this term, or I understand this term right here. For some reason, it gets real messy. Basically, I'm trying to say that here we have our step one. Then say for instance I get stuck at step 2. I'm going to ask a question. Matter of fact, I probably do ask a question. Let's just not use this. Let's go all the way up here where they start giving us steps and flips. Right here, right? I get confused. Or something. What do I say? I ask for a definition. Like, yeah, I don't know how to. here, I asked some random question, right? I only understood some part. I go to some question. Got cross product term, blah, 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 blah. Another clarification, blah, 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 blah. Where did DZ come from? Another clarification, blah, 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 blah. Please explain to me part B like I'm a beginner, right? Maybe I'm just lost the entire thing. Here, we have all of our steps, right? Explain why left side is 0. Clarification. Are you saying T is parallel to ZV? Another clarification, 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 right? And maybe I navigate back. I need to reference things in the past. I think it's important that, first of all, nav exists. Like, I want to be able to like go back to following what steps that it gave me before, and I find that difficult. Obviously, this is the current state of nav as far as that goes. That or like something like this, and you know it repeats. If I search up step, how many instances of step do we have? 15. And some of them are right here. You know what I'm saying? Right? There's. It's not very user friendly. So, first thing, let's navigate this context window. So important. Second of all, I don't understand the full splur, the full 1, 2, 3 that it gives me sometimes, right? So I hit one of these, right? I'm still confused because you just like start over from the beginning. I still don't get it, right? Some part. I still don't get some part. Like you've never seen it before. It does stuff like that, right? It clarifies, it does that. It would be so much easier if maybe you understood a part of it. You could either mark that you did or didn't, or mark, and if it didn't, it will clarify. As simple as that, and you can navigate back. Something like that. Like that's just so much more user friendly, and obviously like your definitions get stored. And that's basically what my product is that I'm building. And I'm gonna be taking time off tomorrow. Not tomorrow, I'm gonna be taking time off, period. And building product like crazy. I need to build this thing out fast. Because it's actually what I need. It's actually what I feel like learners need. Like it's just so much more navigable. Because I mean, like I'm not gonna say I'm fed up. Like because I just wish it was easier to use. As simple as that. So yeah, let's get to the problem now. Let's go. He's buffering. Let me just go grab a drink. Water to specify. Imagine I'm just so fed up with drinking whiskey. Or something stupid like that. I'm just so fed up with my GPT shirts. I need a drink while I learn my rocket science. No, it's water. Come on. Load, load, load. All right. Remember that we got this. Do I remember that we got this? Yeah, I believe I do remember that we got this. Fine. Good. Vorticity is equal to 0. Substitute into the equation above. Got it. Now we'll buy these things. Hmm. Got it? Oh, that's actually easy enough. If the derivative of something is 0, then it's constant everywhere else. So what was the question asking? Are we even asking the right thing here? You can also just pull up the. I'm gonna have to do it here too, but I'm gonna pull up the problem set over here. I don't like how they're grouping. One sec, I got a message about the post that I made. It might have gotten unchecked by the algorithm because it doesn't. It used like a little 5 second clip of an artist, like Espresso by Sabrina Carpenter. I made a little here. Rocket science. And yesterday we managed to get through a big problem, proving that pressure is constant in a streamline using Euler's flow equations. It was conceptually heavy on the linear algebra. The LLMs were working overtime with all of my questions. Right here. As far as pure linear algebra, and just to keep this at a high enough... That might have... I think I might have messed up. That's my bad. Like, I didn't mean to... And for example, in rockets, it's essential for guidance systems and alignment errors, making sure that the rocket is upright. ChatGPT and Claude, these big transformers, are literally layers and layers of matrix multiplications. And obviously, it's more nuanced than that. Whoops. I didn't mean to... That was... That's okay. But anyways, today we're going to be applying curl and vorticity to our understanding of the flow equations and Bernoulli's. Hopefully that resolves. I mean, that would be so nice if that wasn't the case. Otherwise, we're all right. One sec, I'm just clarifying this issue. This is work related. Okay, definitely got messed with on TickTick. We have to do this. Here, let's go over here. We'll do it later. We'll do it later. Let's get back to the navigation. The parenthesis. Nope, it's hallucinating. Sometimes you just need to know when to hit one of these. No, thank you. Let's re-explain it to it. I'm not as mad about this feature because I know that GPT is gonna act up here and there. So let's just do. Oops. Okay, let's go. Incompressible fluid density doesn't change, so good. Inviscid. Got it. The curl of a gradient. Curl operation kills any pressure gradient. Probably ask this healthy question. Oh, vorticity is literally the curl of velocity. Oh my god, dude. These are vector notations, not. I'm still in like x is equal to multiply. Hello. Hi. Dot product is divergence. Cross product is curl. Good. I wonder where they got this. Cross product of the derivative. Is that what the Nabler is asking for? Hmm. Is it really? Did we already arrive at it? I think we just rearranged the terms for that function. Yeah. Okay, fine. After curling both sides, one of them just cancels out, is it? Nabla by a delta p term on top. So that cancels out. Okay, fine, good. So this left side is left with 0. Because the question here is, Mm. They give us that identity? Yeah, they do. Taking curl kills the gradient term. Mm. Got it. Got it. Got it. Got it. Hmm. So with okay, good. It's advection. This is the advection term, it seems. This is the advection term. Oh, just a definition. Okay, so this is the advection term. Move to the left. Take absolute derivative. Oh. These are divergencies. The answer to this is just the delta b terms. Because this is equal to 0. I do not know this though. Cool. My favorite part. Let's go down I like to end the streams with something a little bit lighter, so. I already watched these actually. I went to sleep kind of learning them.
In the last video, along with the ideas of vector addition and scalar multiplication, I described vector coordinates, where there's this back and forth between, for example, pairs of numbers and two-dimensional vectors. Now, I imagine the vector coordinates were already familiar to a lot of you, but there's another kind of interesting way to think about these coordinates, which is pretty central to linear algebra. When you have a pair of numbers that's meant to describe a vector, like 3, -2, I want you to think about each coordinate as a scalar, meaning think about how each one stretches or squishes vectors. In the xy coordinate system, there are two very special vectors. The one pointing to the right with length 1, commonly called I hat, or the unit vector in the x direction, and the one pointing straight up with length 1, commonly called j hat, or the unit vector in the y direction. Now, think of the x-coordinate of our vector as a scalar that scales I hat, stretching it by a factor of 3. And the y-coordinate as a scalar that scales j hat, flipping it and stretching it by a factor of 2. In this sense, the vector that these coordinates describe is the sum of two scaled vectors. That's a surprisingly important concept, this idea of adding together two scaled vectors. Those two vectors, I hat and j hat, have a special name, by the way. Together, they're called the basis of a coordinate system. What this means, basically, is that when you think about coordinates as scalars, the basis vectors are what those scalars actually, scale. There's also a more technical definition, but I'll get to that later. By framing our coordinate system in terms of these two special basis vectors, it raises a pretty interesting and subtle point. We could have chosen different basis vectors and gotten a completely reasonable, new coordinate system. For example, take some vector pointing up and to the right, along with some other vector pointing down and to the right in some way. Take a moment to think about all the different vectors that you can get by choosing two scalars, using each one to scale one of the vectors, then adding together what you get. A completely reasonable, new coordinate system. For example, take some vector pointing up and to the right, along with some other vector pointing down and to the right in some way. Take a moment to think about all the different vectors that you can get by choosing two scalars, using each one to scale one of the vectors, then adding together what you get. Which two-dimensional vectors can you reach by altering the choices of scalars? The answer is that you can reach every possible two-dimensional vector, and I think it's a good puzzle to contemplate why. A new pair of basis vectors like this still gives us a valid way to go back and forth between pairs of numbers and two-dimensional vectors, but the association is definitely different from the one that you get using the more standard basis of I hat and j hat. This is something I'll go into much more detail on later, describing the exact relationship between different coordinate systems, but for right now, I just want you to appreciate the fact that anytime we describe vectors numerically, it depends on an implicit choice of what basis vectors we're using. So anytime that you're scaling two vectors and adding them like this, it's called a linear combination of those two vectors. Where does this word linear come from? Why does this have anything to do with lines? Well, this isn't the etymology, but one way I like to think about it is that if you fix one of those scalars and let the other one change its value freely, the tip of the resulting vector draws a straight line. Now, if you let both scalars range freely and consider every possible vector that you can get, there are two things that can happen. For most pairs of vectors, you'll be able to reach every possible point in the plane. Every two-dimensional vector is within your grasp. However, in the unlucky case where your two original vectors happen to line up, the tip of the resulting vector is limited to just this single line passing through the origin. Actually, technically there's a third possibility too. Both your vectors could be zero, in which case you'd just be stuck at the origin. Here's some more terminology. The set of all possible vectors that you can reach with a linear combination of a given pair of vectors is called the Pauli vector. In the unlucky case where your two original vectors happen to line up, the tip of the resulting vector is limited to just this single line passing through the origin. Actually, technically there's a third possibility too. Both your vectors could be zero, in which case you'd just be stuck at the origin. Here's some more terminology. The set of all possible vectors that you can reach with a linear combination of a given pair of vectors is called the span of those two vectors. So restating what we just saw in this lingo, the span of most pairs of 2D vectors is all vectors of 2D space, but when they line up, their span is all vectors whose tip sit on a certain line. Remember how I said that linear algebra revolves around vector addition and scalar multiplication? Well, the span of two vectors is basically a way of asking what are all the possible vectors you can reach using only these two fundamental operations, vector addition and scalar multiplication. Only vectors whose tip sit on a certain line. What are vector addition and scalar multiplication? This is a good time to talk about how people commonly think about vectors as points. It gets really crowded to think about a whole collection of vectors sitting on a line, and more crowded still to think about all two-dimensional vectors all at once, filling up the plane. So when dealing with collections of vectors like this, it's common to represent each one with just a point in space. The point at the tip of that vector, where, as usual, I want you thinking about that vector with its tail on the origin. That way, if you want to think about every possible vector whose tip sits on a certain line, just think about the line itself. Likewise, to think about all possible two-dimensional vectors all at once, conceptualize each one as the point where its tip sits. So, in effect, what you'll be thinking about is the infinite flat sheet of two-dimensional space itself, leaving the arrows out of it. In general, if you're thinking about a vector on its own, think of it as an arrow. And if you're dealing with a collection of vectors, it's convenient to think of them all as points. So, for our span example, the span of most pairs of vectors ends up being the entire infinite sheet of two-dimensional space. But if they line up, their span is just a line. The idea of span gets a lot more interesting if we start thinking about vectors in three-dimensional space. For example, if you take two vectors in 3D space that are not pointing in the same direction, what does it mean to take their span? Well, their span is the collection of all possible linear combinations of those two vectors, meaning all possible vectors you get by scaling each of the two of them in some way and then adding them together. You can kind of imagine turning two different knobs to change the two scalars defining the linear combination, adding the scaled vectors and following the tip of the resulting vector. That tip will trace out some kind of flat sheet cutting through the origin of three-dimensional space. This flat sheet is the span of the two vectors, or more precisely, the set of all possible vectors whose tips sit on that flat sheet is the span of your two vectors. Isn't that a beautiful mental image? So what happens if we add a third vector and consider the span of all three of those guys? A linear combination of three vectors is defined pretty much the same way as it is for two. You'll choose three different scalars, scale each of those vectors, and then add them all together. And again, the span of these vectors is the set of all possible linear combinations. Two different things could happen here. If your third vector happens to be sitting on the span of the first two, then the span doesn't change. You're sort of trapped on that same flat sheet. In other words, adding a scaled version of that third vector to the linear combination doesn't really give you access to any new vectors. But if you just randomly choose a third vector, it's almost certainly not sitting on the span of those first two. Then, since it's pointing in a separate direction, it unlocks access to every possible three-dimensional vector. One way I like to think about this is that as you scale that new third vector, it moves around that span sheet of the first two, sweeping it through all of space. Another way to think about it is that you're making full use of the three freely changing scalars that you have at your disposal to access the full 3 dimensions of space. Now, in the case where the third vector was already sitting on the span of the first two, or the case where two vectors happen to line up, we want some terminology to describe the fact that at least one of these vectors is redundant, not adding anything to our span. Whenever this happens, where you have multiple vectors and you could remove one without reducing the span, the relevant terminology is to say that they are linearly dependent. Another way of phrasing that, these vectors where two vectors happen to line up, the case where the third vector was already sitting on the span of the first two, or the case where two vectors happen to line up, we want some terminology to describe the fact that at least one of these vectors is redundant, not adding anything to our span. Whenever this happens, where you have multiple vectors and you could remove one without reducing the span, the relevant terminology is to say that they are linearly dependent. Another way of phrasing that would be to say that one of the vectors can be expressed as a linear combination of the others, since it's already in the span of the others. On the other hand, if each vector really does add another dimension to the span, they're said to be linearly independent. So with all of that terminology, and hopefully with some good mental images to go with it, let me leave you with a puzzle before we go. The technical definition of a basis of a space is a set of linearly independent vectors that span that space. Now, given how I described a basis earlier, and given your current understanding of the words span and linearly independent, think about why this definition would make sense. In the next video, I'll get into matrices and transforming space. See you then.
All right. We'll go ahead and end stream right there. Yeah. I want to get to building.